So, my name is Nicolai Josuttis. I'm talking about C++17. The interesting thing is C++17 is just a bunch of a lot of new little features, but the real power comes from combining them, and I want to show you that by 4 examples. As you probably know, C++17 is one step further in the evolution of C++. We now have a 3-year cycle. So the 3-year cycle means whatever feature is ready on time will be delivered, as in a time box-driven software project. The next delivery will be C++20, which now has feature freeze. And yes, so there's a big history, and some of my books cover this. So before I start, I have to start with the first slide. I always have to start now. I have to talk about the way of initializing an object. So we had the C way, the C++ way, and the old C++ way, the new C++ way using curly braces. So the question is, what do I use? And I use curly braces. And sometimes I use an equal sign, and I just want to have 1 minute to explain why. It always works to initialize an object if you pass no arguments. It detects narrowing. It is self-explanatory. It is works in areas where all other or some other pieces of initialization do not work. For example, to initialize a member in a class, you can't use parentheses. And there's no other ways to initialize an enum other than using braces. And it's the way aggregates are being initialized. So don't be surprised that I use braces in all my examples. So this is, by the way, not the recommended way of the community. The community is highly diverse in the way how we should initialize an object, one of the nightmares we have now in C++. So let's start with the first example. Let's talk about if and trades and guards. Here's an example of a function you can question whether it's very useful, but it's more that I demo some issues of the C++17 here. And the example is I want to insert in a generic function an element in a collection. So the first argument is a generic element, and the second one is the generic collection. However, I use pushback, so this essentially only works in a vector and in a deck and in a list. And so let's use it. Let's, for example, create a vector. And in this vector of strings, we want to insert a string. OK, compiled. Fine. Great. Can I do something more interesting here? Oh, yeah. I want to insert an int in this collection. So what would I have to do? Or what can I do? Well, I can say, well, there's an overload of this function template saying I take an int. The problem, though, is that this will not work nicely for an int. So for this int, we now call toString, but it will not work for a double, because for a double, the first function is a better match than the second, and also if we convert it to an int, we lose some value. So we need another overload to insert a string, and that might apply to a couple of overloads we have. So can we do it better? Well, yes, let's use an if inside the function, and let's use in this if. The question is my passed object of an arithmetic type? And if it is, we convert this arithmetic type to a string. Otherwise, we just try to push it back. So does it work? Unfortunately not. If you try to use this function, you get compile time errors whatever you try. Because what you're using here is a compile time if, and runtime if, excuse me, thank you. And the runtime if is only used at runtime. So at compile time, all the statements have to be valid when we instantiate this function. So for example, if you try to compile the first example, you get a small error message. And in the small error message, they essentially say, we tried out a couple of things, but nothing worked. So what's the first new feature here? A compile time if. With this compile time if, you can say, OK, let's insert, let's call pushback with toString if it's an arithmetic type, and otherwise use pushback. Fine. First problem solved. Since C++17, you can write the expression saying, a type trait saying, is this arithmetic, then the type, and then colon value, a little bit shorter, to say, is arithmetic underscore v. OK, let's improve this a little bit, and let's use mutexes, because we have a multi-threaded environment. So let's do it while the vector is locked. OK, so we might have a mutex, introduce a mutex where we get access to the vector, and then we might use a lock guard to say, before we try all these insertions, let's lock it. So the next thing we can do better in C++17 is we no longer have to specify, once again, the type of the mutex when we declare the lock guard. That's called class template argument deduction, and it means that even in class templates, you can now deduce the type of template parameters. In this case, it's the type of the mutex used, so that you can just write what you want. OK, however, it might be that we have other things to do in insert a string. So the piece of code you see in insert a string is only some piece of code, and we might do something in front, then we might do something behind inserting the element. And then it's not the best strategy to use mutex that locks the vector for the whole time. So let's lock the mutex inside the function. So we might extend the API of this insert a string function and say, OK, let's add an additional argument, which is the mutex to lock, so that the caller can pass the mutex for the vector. And then inside the function, just for the if statement, during either pushing back the element converted to string or the other pushback, let's then use the lock guard so that the vector is only locked at this little piece of moment, at this protected region. So don't forget to put braces here, because we want to make sure that right after the pushback, because the lifetime of the lock guard has ended, the mutex is unlocked. Can we do it better now with C++17? Yes, we can. We can use an if construct, a compile time if you just saw. So we can say we have a compile time if, but this if looks different than the one before. Look at that. It has a semicolon in the middle. And this is a new way of that is supported now in C++17 if with initialization. We can also add an initialization to switch now. For those who ask me, can you also have an initialization at while now? Yes, we have that for years. It's called for. And yeah, so we have that now. And it even works with at compile time. And now this is tricky. Look at that. At compile time, we evaluate the condition, but the initialization is done at runtime. That's OK. That's allowed. This is a compile time if. In both cases, in the then and the else case, we have a runtime initialization of the lock guard. But we decide at compile time whether we compile the then or the else case. That's supported. So that's a new if with initialization. Beware a little bit. Well, first of all, can we improve that even better? Yes, there might be an issue that we might not need a mutex, or that we might need multiple mutexes for whatever reason. So we have a new variadic log guard now, and it is called scope log. And what you can now even improve here, you can say, let's pass an arbitrary number of mutexes to this function that might be logged while we call pushback. So you might still pass one mutex, but you might also pass two mutexes. Note that these mutexes might have different types because this is a variadic template. Or you might, and by the way, if we have multiple mutexes here, then the scope log that logs the mutexes uses the standard function stdlog, which has a deadlock avoidance mechanism, so that we try to avoid deadlocks here, only here, not in general. You can still create deadlocks yourself. And so that we have better safety here in our code. And you can pass no mutex at all, and that's also supported by a scope log. If there is no mutex passed, then it will not log anything. So this code is essentially now generic in a way that we might even not log a mutex at all. And that gives us some flexibility you might be happy about in your code. Okay, so look at this, the next step. Look at that. The initialization, you might say, we can improve. The initialization of the scope log here in the if construct expression. That's LG. LG is initialized by a couple of mutexes, and that performs the log for all the past mutexes. So do I need the name of the log guard? Well, no. From a programmer's perspective, I don't need the name. So let's improve this version and remove the name. So let's create a temporary log here. Well, or multiple temporary logs, depending on how much mutexes we passed. Unfortunately, this is not an improvement, because what you have done here, you have created a temporary log object, a log guard. The lifetime of this log object is not until the end of the control structure. It's until you find the semicolon. So even before the condition, this log will be unlocked again. So, and there's no compile time error on that. It will just not log, and probably at runtime in production create some interesting issues. So don't do that. That's a fatal runtime error. Please give it a name, and that's it. That's more or less every combination I want to introduce here. So you have seen here, I think, 5 or 6 different new features just in this one line, in the if const expo line. So you're using a compile time if, you are using an if with an initialization, you are using a scope log, you are using isArithmeticV as a shortcut, and you're using class template argument deduction because you don't have to specify the type of the mutexes when you declare the class template object scope log. So that's nice. That's a little improvement. And by the way, yes, C++ would not be C++ if with a new feature we wouldn't introduce new traps. And that's all here. By the way, this is not a new trap. If you do the same in a for loop, you would run into the same problem. So if you use the initialization in a for loop, having no name for the log, you haven't logged via mutexes during the for loop. So don't do that. Okay, there are other traps, though, we have to talk about. So class template argument deduction is a little bit funny. It can be used very well, like in the example of these logs and log guards, but beware if initialization becomes complicated and follows complicated rules. So yes, if you declare a vector of, you don't say what it is, and you pass some curly braces here saying this vector is initialized by 2 ints, class argument deduction, class template argument deduction will deduce that this is a vector of int, and that also works for one element. If you don't use curly braces here, then the initializer list constructor is not used. So we will still deduce a vector of int, but the int has 8 elements of the value 15. And if you have just a value not passed with curly braces, this will not compile because overload resolution will find the constructor that is marked with the arrow now. And in this constructor, from this constructor, the one before, and the one before the arrow constructor, that cannot be used to deduce type T. So this will not compile. But you can initialize, you can try to initialize 8 elements of a string literal. So does this work? The funny thing is here, it works when we consider deduction. So we will deduce the type of T. We will find out that the type of an element is, what is the type of this empty string literal? It's a constant array. It's an array of constant characters, and the array has a size of 1 because we only have the null terminator here. And now it's important that the constructor takes this argument by reference, and because it takes it by reference, it does not decay. So this type does not decay to become a const char pointer. It has a type as I just said. So type T is deduced to be a character 1. Oh, the const is wrong here, by the way, because the const is in front of the T anyway. So T is deduced to be just an array of 1 character. And that, unfortunately, will be deduced, but it will not compile because you can't instantiate a vector with an array. That's it. Okay, other examples here. I skip that. It's good enough. There are more problems to show, but we already run out of time to demo all the problems. Next problem. Every problem has 15 minutes, roughly. Every example, did I say problem? No. Feature, cool feature. Okay, next example. Variadic templates. Let's use variadic templates. Variadic templates were introduced in C++ 11 so that you could write functions like this. You can say I have a print function on the bottom here, and the print function takes 1 argument or an arbitrary number of additional arguments. And so we can pass 3 arguments. The first argument is always printed, and the next one is passed to recursively passed to print again, to print it out. And that we recursively instantiate. So at the end, we essentially have to compile or create assembler code for printing out all the arguments we passed to print. That's nothing new in C++ 17 here. But we have a problem here in C++. And the problem is recursive instantiation. Recursive instantiation takes a lot of resources, and the compiler takes time, and is something we try to avoid. So can we do it better? Yes. We have something new. Oh, first of all, the first question might be, for the end criterion, which is here an empty print, can we use runtime if? No. That's not allowed, but we can use the compile time if. You find the compile time if here to end this recursion so that you don't have to need an empty printf at the end. However, can we do it better than this, than recursively instantiating templates, function templates? And yes, we have a new feature called a fold expression. You can say, if I have a variadic number of arguments, so what we call a parameter pack, this you can say that we apply a certain operator to all of the arguments, like here saying all of the arguments should be combined with the operator plus, and that means you can pass a different number of arguments of different types as long as plus is allowed to call. This will compile and concatenate or add all the values here. The problem here is if you don't pass no argument, then we have no value here. But for that reason, you can say I have an initial value like 0, so that even works then for the case that we don't have any value in the parameter pack. Good. So that new feature can be applied to our print function, and we can replace the whole recursive instantiation by just this, saying, okay, this is print all. For all the arguments, we print them out to cout. That's it. The syntax is parentheses, dot, dot, dot in the middle. On the left, we have the initialization. On the right, the parameter pack. And then you have to pass which operator to call. It has to be the same on both sides. So we essentially compile and say, let's print out all the values. We don't recursively instantiate that. That compiles a lot faster, way faster than before. And yeah, we have our output. Oh, wait a minute. There's a space missing between these arguments. So how can we fix the space? Well, we can easily extend this expression. You can say at the end of this, there should still be a new line. That's fine. But you can't extend the syntax or change the syntax of this operation. It needs a syntax, braces, initializer, 2 times the operator, dot, dot, dot in the middle, and on the right, the parameter pack. Well, but the parameter pack can be an expression. So you can say something like this. Let's print out all the arguments. And for the arguments, but I call a helper function that prints out a space before the argument, the next argument. Well, and we don't want to do that for the first argument, of course. So we now introduce a special handling saying the first argument, if it comes, is printed out. And for all remaining arguments, we print them also out by calling a helper function space before, which prints out the space, returns our argument, and then we print out the argument. Okay? Don't take a picture of this. We are not done. So, yes, this works because this effectively compiles something like this. We print out the first argument, and we print out then for the further argument that we called space before. But wait a minute, there's an issue. If you, the yellow box here, if you would have implemented that just as a piece of code in C++ 11 or 14, you have 2 different possible outputs here. That is, you might either print hi space 7.5 space world, or you might have the output hi 2 spaces 7.5 world without a space in between. Because we have no guaranteed evaluation order here regarding the fact when an operand here is evaluated. So the evaluation of space before, printing out the space, might happen for both arguments before we start actually to print out the rest. So the results of what was printed out, what was returned by space before. However, this is fixed with C++ 17. Yeah, we have for this reason to make this compile, not for this example, but there are other examples. We have introduced now some constraints on the operators we have already. So you see in red here the changes we made. We have now a guaranteed evaluation order for some operators, like dot and arrow from left to right. Function calls now guarantee that the left side of the function, so the name of the function, is evaluated before its arguments. The argument order is still undefined. And then we have evaluation order also for the output operator and input operator, which we just use, and also for the assignment operator. We didn't define an evaluation order for all the other operators. That there was a big fight, and for those who like fast compilers, they said, oh, that's too much, because we pay a price not using the ideal way to evaluate expressions. So that means this is now guaranteed to work. By the way, note that we still don't have a guaranteed evaluation order in function arguments. So if you pass them as arguments to a function call, you might still get 2 spaces in a head. Okay, that's it. Let's use it. However, can we make it better? Yes, we can, but we have to solve a problem. And the problem is you can, as you just saw, use expressions to parameter packs. And then this expression is used for all the arguments. So besides saying, if I take an arbitrary number of arguments, I pass them all to foo, you can say something, for example, like this. You can say, I pass to foo for each argument added to itself as a comma-separated list. That's nothing new in C++ 17. That's already supported in C++ 11. However, what a lot of people tried out is, let's call foo for each argument. And the problem is, this does not compile. And can we do it now in C++ 17? Yes, you can. This is a way to do it. You say, you use a fault expression, and you use it with a comma operator. So you create a sequence of comma-operated calls to call for each argument to call foo. And that's the way you can do it now. Please note that this strange feature that we can overload the comma operator might create trouble. So each time you call a function where you don't know what it returns, you should cast it to void. By the way, I learned in the meantime, there was a workaround before C++ 17. It looked like this. So you could take the guaranteed evaluation ordner of initializing an initializer list to extend an initialization for a list to call all the foo arguments. You needed the comma there because at the end you had to initialize an initializer list of int just to throw it away. So that was a workaround that did work even in C++ 11. I think the new way is a little bit more readable than before. And of course, the new way we can use with move semantics, then it looks like this. So what does it mean? In our example, print all the arguments, but have spaces between them. Use a comma operator. Use a lambda that prints out a space and the argument, and do that. Good. Can we do it better? Yes. Here we have a space we have between the arguments. We want to be more flexible here. So let's introduce a new template argument saying let's have a character here. And the default value is a space. So we can call print by default having a space between the arguments. But we can change this. And now a new feature is called auto here. So you can have different types here. We have now a new feature saying that the template, a non-type template argument, can be declared with auto, which means you can decide as a caller what is printed beside this. So we could now pass to print as a template parameter 42. So between each argument there would be written 42, which might not be very useful here. But we have another feature, which is you can now have local strings defined with no linkage and pass them directly to a template. And that way, you can say, let's print all the arguments with even a string literal in between. And that works now. We are still waiting for that. You can directly pass in the template argument the string literal. That will probably come, as far as I know, in C++ 20. OK, and for those who hate semicolons or having something in two statements instead of one, you can do it in one statement, define the lambda, and use it in the folder expression to apply this lambda to all the arguments in print. OK, just one comment here. We use this feature also in the standard for argument deduction. For example, we have what we call so-called a deduction guide specifying if you have an array of an arbitrary number of values, not specifying the type of the elements, we deduce, that's a new feature also we deduce that all the elements in the array have the type of the first argument. So we have a special name for the first argument. And then we also deduce that we have 9 elements because it's the number of further arguments plus the first argument. However, to avoid that we have used this feature when we initialize with different data types, we have here, say we disable this deduction guide. So we disable this automatic deduction if all the elements don't have the same value. And what we use here is a fold expression saying, well, for all the template arguments, we have to check whether all the later arguments have the same type as the first argument. And if it's not the case, we disable this deduction. Okay. Time is good. Third example. Let's use a vector of strings, and let's initialize a vector of strings with some IDs, with some strings where we have a prefix, either being a lowercase ID or a capital case ID, and then a value, an integral value converted to a string. So we get a sequence of values like you see here on the right in the bubble. Let's sort them. So that's fine, works fine, you will get a result. That's not the point. Let's sort them ignoring the first two characters, because we want to ignore the prefix, which would give different results. And this takes significant time. Here you will see why, or you will see how it takes significant time. We would say, let's use a substring of the string. The problem is the substring function for a string creates a new temporary string, and even if you have short string optimization so that no heap memory is involved, that is complicated, or that takes too much time and effort, so that we more than double the speed of this sorting by just ignoring the first two characters. So can we improve that? Yes. We have a new beast called string view. String view creates just a view to the string, and this view does not create a new string because it does only refer to the characters of the underlying string. And if we then in this view take a substring, we make it faster because we don't create a new string, we only reduce the view to the string. So let's see, and you see that we roughly have around the performance we had in the original sort, not dealing with substrings. I have to say something about string view here. Before we continue with this example, let's have a break and go to string view. This is how string view is working. If you have some value in your system, a string literal, you can create a string, which means a string creates a copy of the value because it owns the whole value. It's a value type. Or you can now have a string view saying, I don't own the value, I only refer to it, which is fast but dangerous. So string view is like a raw pointer. If you see the word underscore view in a program, you have to get scary. That's a smell. That's a smell like using pointers. You run into the same danger. Yes? Once for your life, learn that, please. And however, there are safe usages, but you have to be very careful with that. You can even implicitly create a string view from a string. Please note that the thing on the top, a string view from a string literal, is safe because as this string literal has a lifetime for the whole program, you will never refer to something that is not owned by you, while the string view to the string depends on the lifetime of the string you refer to. And that's some danger that you make mistakes. Here's a nice piece of code that demonstrates how easily you can fall into traps now. Let's create a string view referring to the string literal hi. And then somebody in your team, in your project, has written these 3 lines of code, which say, let's add a string view to another string view. Well, the guy who wrote this function made everything right. Don't return a string view here, that would be wrong. Because we have now created a new string that has to refer to new memory, we create a string, an SCD string. So we convert the two string views to a string, concatenate them, and return the string, a temporary object that is a string. And that's fine so far. Now, a third guy in your project has written a cool function template. Let's add two elements of a type and return the sum. Yeah, this looks safe. Add two ints, you get an int. Add two strings, you get a string. What's the problem? So the problem is, let's use this template for my string view. And so my string view is passed twice to this function sum, which calls the plus operator. The plus operator will create a temporary string, and the temporary string is the outcome of the expression x plus y in the template and return it to the caller. However, the return type is t, and t is the type we passed in. And the type we passed in was a string view. So what do we return? We return a string view to this temporary string, and then the temporary string is destroyed, so that's what we return. That's not fun if you use it. If you're lucky, you get a corner. So who made a mistake here? Well, we can argue whether an implicit type conversion from string to string view is a good thing. Who made a mistake here? It's clearly the guy in the middle, because he made an assumption which was wrong. The assumption was that if you concatenate two objects of type t, the outcome is a t. And that assumption is wrong and dangerous. So please don't make it. Let the compiler find out what the real type is. And this is also one of my slides I always demonstrate when I explain to people why it's so important to use auto and function templates. It's correct. Maybe not that readable, but it's correct. And that's more important. And even if inside you have a temporary object for the sum, use auto there. So auto is your friend in templates, even as a return type. So if you have a style guide, avoid auto. It's wrong if you implement templates. Good. By the way, we know this problem. We're getting a lot more problems like this in the standard, because we introduce a lot more types now that have no value semantics, that have reference semantics like string view, span. If you read the suffix underscore span in C++20, that's as dangerous as underscore view. So they are all dangerous. And we have a problem now, because we will run into these problems. We have seen that already, people falling into this trap. So we thought about how to solve that. The only way we can solve that is that in an interface of a function, we can express lifetime dependencies. So in the function that would convert a string to a string view, we have to specify that the resulting string view, the lifetime of that depends on the lifetime of the string you passed in. And when we can do that, and I hope we soon can do that in C++, then we can detect this problem at compile time, not using valgrind or so. At compile time, we could detect this problem. Well, there were different proposals to go that path. One proposal was by Herb Sutter, another was by Richard Smith and me. Herb Sutter's team implemented already an experimental solution of this. If you haven't heard about that, please look at it. That's Herb Sutter's lifetime profile. This is a tool that implements the way that you can specify lifetime dependencies in function calls. And that way, you can detect the problem I just demoed to you. Here on the left, there's a Godbolt implementation with this extension. And we see exactly what the problem is if we turn on -w lifetime. So you get the warning about what I just explained to you. I think this is a very, very important tool for your quality gates before you deliver software. because it will be very cheap, because you don't need complete task coverage with Valgrind and runtime. It's a compile time feature that detects several bugs in your programming code. Good. So coming back to our example, we learned string view is your friend if you use it wisely. And that's fine here, because we only create a temporary string view for the strings we sort, and all the strings exist until the end of the sort algorithm. So that's fine here. Can we improve this even better? Yes. We can use parallel algorithms. So we have a new extension now in C++ 17 that says you can parallelize algorithms. So this is essentially calling the sequential model, but we can now switch to parallel execution of this sort. And now look at the numbers, which are not representative, which are not precise. It's on my laptop, my numbers, having run it several times. But you see there is significant speed up. In this, even in this small example, only having, 1 million elements, you see that you are even better than the initial version by a factor of 2.5 better than the initial sort without the substring feature. So yeah, we have something. The bad thing is that you can't specify how many threads are used and which constraints are there. It all depends on the implementers of this library. Things like that will come later in later C++ standards. It's there. So the only way to validate whether it's worth it to parallelize this or not, measure on the platform you use with the typical scenario you have. When I learned about parallel algorithm, I raised one question. I said, why the hell do we have a parallel partial sum function now? Because here's the it's a partial sum algorithm. It says, let's compute for a sequence of values all the partial sums. So the first result is 3, the next is 3 plus 1, the next is 3 plus 1 plus 7, etc. That way we convert relative values, for example, to absolute values or so, which is pretty common to need, because we might try to find a threshold where the bar was too high when we had added different values. So that's an algorithm that's widely often used. And we have a parallel version of it in C++ 17. It has a new name, because we guarantee evaluation from left to right for partial sum, which would rule out parallelization at all. But I would say we also rule out parallelization because we have to start from left to right, because we have to start with the first and second. We need all these results. But what I learned is that parallelization is nice, because sometimes you can invent better algorithms than before. And there's a way to parallelize this. I'll show you how. If you have this sequence, I extended the sequence by another 8 elements. And the way you parallelize to compute all the partial sums is not to start with the first partial sum, then the second, etc. You do the following. You sum up all the intermediate sums, first of all 2 elements, then of all 4 elements, then of all 8 elements, etc. So you compute a binary tree of all the sums, and then you go down and use this information to compute the final values. And as you see, in all the steps here, everywhere where we use here on the same level multiple computations, they all can be computed in parallel. So we have to change the algorithm to come from a naive implementation to something interesting. But the result is that the computing of a partial sum can be 10 times faster if you have, a CPU with 30 cores or so. And we see that in practice. And so that I found interesting. So there's more than just the naive thinking of this can't be parallelized. So you can benefit from this knowledge. And please note, we don't need any additional memory here. We don't have to compute allocate memory to get the result. We just use the memory we have. Okay, last example. Unions, polymorphism, overloading lambdas. That's one of my favorite, and it solves the following problem. If we have polymorphism the classical way, we would implement this with inheritance, saying I have a base class, geometric objects, and two concrete class, circle and line. So let's create an object, and the problem is, to have polymorphism, you need a vector of pointers, and because it's pointers, you need u, because otherwise, after the creation of the vector, the element might be destroyed, but you still use the pointer. So you come up with something like this. You might initialize a figure of different geometric objects, calling new everywhere, and then push it back, return it, and then you use it. And then at the end, don't forget, before you remove all the elements in the vector, that you call delete, because otherwise you have a memory leak. And yes, you can improve that a little bit by using shared pointers and unique pointers, which have their own problems. So you can replace this problem by another problem, which might be less, but there are significant problems. Shared pointer have a performance problem, and the unique pointer have some restrictions regarding what you can do. For example, you can't do a downcast, a dynamic cast on a unique pointer. So, is there an alternative? And the alternative, surprisingly, comes with C++17 with a new data type, and the new data type is called variant. And this is a kind of a new type for union. So a variant is, I am either an int or long or string. Now you might say, wait a minute, we have a union already in C and C++ with the keyword union. So what's the cool thing here? The cool thing here is this union knows what it holds. And it has a slightly improved API. So instead of saying, let's set the value as an int or as a long, you just say, assign a string, assign 42, assign a long, and automatically the assignment will find the best match here and use this value, and the union and the variant then knows what it holds. So if you ask now the variant, what are you holding? It will give you the index of this information and say, I'm holding a string, or I'm holding a long, etc. And by the way, you see that even implicit type conversions are possible. You assign a string literal, and the best match for a string literal is std string, so this is used. And then if you know that, you can access the value by different ways. One is calling get, and if you then use the wrong index or an invalid index, you either get a runtime or compile time error. That's it. So how can this help us? Our example, our fourth example, saying, let's use polymorphism. Well, we have a variant here. We can say, in my vector, I have elements that are either a circle or a line. That's all what we say. So we introduce a helper type called I'm either a circle or a line, and I use that as the element type of a vector. Now the interesting thing is a variant has value semantics. So if you put in a vector, the vector creates a copy. If you put in a line, the vector creates a copy of the line. If you put in a variant that is a circle, it will create a copy of the circle. So you don't run into the problems of lifetime issues because you use references or pointers, and that also means you don't have to deal with new and delete. You just create the things on the stack, push them into the vector, and that's it, and return the vector. And then later on you use it. And now the problem is, how can we bring polymorphism into this, saying, while I'm iterating over all the geometric objects, I have either to call draw for an object or draw for a line. So essentially, the kind of code you have to write is, if the variant holds a circle, call draw of a circle. If the variant holds a line, call draw of a line. That kind of thing. And you should have a good performance. You should not have an if-else chain. You should have smarter things to do that, like in a virtual function table. And here's the way you do that. It's called visit. So with visit, you can say, hey, my dear variant for each and every value. If you take the value, please use this function, or you can pass a function object with multiple functions there and call this code. And this is a generic lambda. So this is a function template that is instantiated for all the types we have. So this generic lambda will be compiled once for circle, once for line, and both will be available in this visitor. At compile time, this visit function checks that all the instantiations are valid, so that each type has a draw function. And then the code will be generated that depending on the index of the alternative, you jump to the right function instantiation of this lambda, and this instantiation will then call draw. That's it. That's a local virtual function table generated by visit for you. And that's it. That way, you have your polymorphic solution. No reason to worry about memory leaks. Everything is on the stack. There's no need for pointers, no new and delete, and note that there's another benefit. All the elements in the vector are now located next to each other. So regarding caching, good caching, this works better than before, because the alternative using pointers means we have pointers which might refer to different locations in your program, so that you have to, that it's more probable that you get page faults and have to wait for getting the corresponding data into your CPU. And wait a minute, we are not using the base term. We are not using polymorphism using virtual, so forget it. You can still have a base class if you have some common information, but you don't need the base class as an interface that is used in your implementation. So you can just have a type called circle, a type called line, and that's it. The third alternative here could be a string, an std string, and it will also work as long as the string has as draw, or we call a common API. Okay. Two questions usually come here. First of all, do we have something, how do we do a downcast here? So let's assume circle has a center, a special function called getCenter. So normally in polymorphism we use dynamic casts. In shared pointers we use dynamic pointer casts. And in unique pointers we have to convert the unique pointer to a raw pointer and call dynamic cast. And so here we have now a different approach. The approach is a function called getIf. GetIf is the dynamic cast of a variant. It says, let's take the address of this variant, because we don't have pointers, and then let's try to convert this to a circle pointer. If this works, we are fine, and then we can get a pointer, a valid pointer address. Otherwise, we get the null pointer. So we use the new if with initialization to double check whether we have a pointer, and if we have a pointer, we use it to call getCenter. That's it. And that's very fast. That's usually faster, I measured that, than the polymorphic approach in using visitors, for example. Here's, by the way, another way to do that. You could come up with, by what you just saw, you could inside the lambda have a compile time if expression, double checking when you currently have the implementation that your auto type is in fact a circle type, which means that your object is a const circle reference. Don't forget constant reference there. Then you can here directly do something. This is decided at compile time, whether this piece of code printing out getCenter should be compiled or not, depending on which instantiation of this lambda is used. So there's another interesting way to overload this, or to implement downcasts. This is this. You can overload lambdas. And this overload of lambdas even works if one of the lambdas is generic and the other is a circle. We might run into some issues because we have the problem of the best match when we have overload resolution. So be very careful if you do that. For example, that all the declarations have all const and all reference, because otherwise interesting surprises might happen. But you can do it. And you can say for all the elements, in normal elements I call draw, but for circles I call center. And that way you could say, if my variant holds an std string, I do something totally different. Now the question is, what the hell is this overload? Well, this is a combination of a couple of new C++ 17 features. It's not standardized. It's something you have to implement, but you can easily implement. And this is the way it is implemented. It's essentially 4 lines of code. What you say here is, I have here a data structure overload that is derived from a couple of functors. And these functors are coming from argument deduction. In the last line, you say, whatever you pass as a template, as an argument to this overload function, please deduce that you take the type of these things you pass as an argument as template parameters. So that says, and that essentially we are saying, I pass 2 lambdas. These 2 lambdas are passed to the overload constructor. This overload constructor says, oh yeah, so these are my 2 template parameters, and the 2 template parameters are my base types. So we derive from all types of all lambdas we have here in this overload, without specifying their types. And then you have to, because each overload implements operator paren, which means, which is a problem if you derive from multiple classes the same operator. It is invalidated, it's not inherited, but you can use a using declaration to still make it available. And we do that, and this is a variadic using declaration, which is also something new in C++ 17. So by having all these features, you essentially have the effect you just saw. Okay? We're thinking about to standardizing it, but we're also thinking there are some things where this doesn't work perfectly. So we are also thinking whether overloading of a lambda shouldn't be a language feature. So that's one reason why this will not come in C++ 20. So this is using std variant, and by the way, what is this also using? It's what you initialize here is an aggregate. That's not a class, that's an aggregate. Aggregates in C++ can now have base classes, and that feature is used here. And we have deduction guides, and we have variadic using. All these features are used to have this. And I have to say that. Here only curly braces work. Don't use parentheses here, because that's the initialization of an aggregate. But I told you already, you should always use braces for initialization, and you're fine. You don't worry about very strange compiler errors messages if you use parents here. That's it. So you have seen several new features of C++ 17, and they are examples. In 4 examples, each and every example used combined at the end several features of what were introduced. Each and every feature is very, very small to some extent, but together we create an interesting amount of power in C++ 17. And that's my message. Combining these features is the key, especially that makes C++ 17 much more powerful than we thought initially, just reading a list of the features. And yes, we introduce new traps. And that's a good reason you buy my book, about C++ 17, to read all about all traps I at least know about. Yet it is now being published close. In 3 weeks it will be published at Amazon as a printing version now. The electronic version was already available for 2 years because it was updated regularly for free for those who bought it. So you might be interested to see these and other details there. And that's the end of my talk. Thank you very much for your attention.